A comet can be a wonder to behold. For thousands of years, these visitors have mystified, enchanted, and terrified humanity. And even today, despite much attention from astronomers, the popular science of comets is filled with enigmas and unresolved mysteries. We long thought of these bodies as mere chunks of dirty ice warming in the sun. But since the beginning of the space age, it seems that the key comet discoveries have all come as huge surprises. What does this continuing stream of surprises mean for the future of comet science? It means that the core theoretical assumptions must be reconsidered. The new facts about comets underscore the long-ignored electrical behavior of the sun. And here the biggest surprise changes the picture of comets altogether. It is not rising surface temperatures and evaporating ices that provoke the dramatic discharging of comets. It is charged particles erupting from the sun to exchange charge with both the coma and nucleus of a comet. And there is much more to this picture because direct evidence will rewrite planetary history as well. It seems that comets are born from the very stuff of planets themselves. They are the residue of shattering planetary catastrophe. Today we can test two views of comets against decades of discovery. We can pose the long unasked question: is a radically new interpretation of comets now required? It was only in the mid-20th century that a scientific consensus emerged on the nature of comets. In 1950, astronomer Fred Whipple proposed a model that came to be known as the dirty snowball hypothesis. Whipple envisioned comets as conglomerates of frozen gases, mainly water, carbon monoxide, and carbon dioxide, together with the primordial dust of the early solar system. But a dilemma had to be solved. Comets lose considerable material at each pass around the sun. This means that the comets we see cannot have been around all that long. So the Dutch astronomer Jan Oort envisioned a vast horde of icy objects circling the sun about 1,000 times more distant than remote Pluto. He imagined that after billions of years, one of these dirty snowballs could be deflected from the icy cloud by a passing star. It might then fall into the inner solar system to produce an active comet. As astronomers came to accept the idea, they called this theoretical source of comets the Oort cloud. But by the 1990s, it became clear that numerous objects circle the sun at much closer distances than the conjectured Oort cloud. Astronomers came to imagine short-term comets originating from a disk of debris called the Kuiper belt, extending outward from Neptune's orbit. But then advanced computer simulations suggested that Kuiper belt objects were too stable to be the source of most short-term comets. One surprise at a time, the origin of comets has become increasingly uncertain. But always it is assumed that comets are composed of dust and ice warmed by the sun to create a coma and tail, leaving a rind of dust. The theory suggests that beneath the blackened, shallow crust, pockets of gas form. At critical moments, the pressure breaks through the surface, creating jets blasting vapor and dust away from the nucleus. But how well does this popular theory explain what we've more recently learned about comets? In an alternative view, comets have a much different history. This view sees comets as debris left by intense electrical activity in an earlier phase of solar system evolution, not billions of years ago, but a much more recent epoch of planetary instability and violence, one that reached even into early human times. This new perspective combines historical facts with surprising recent discoveries about comets. In the electrical interpretation, not just comets, but asteroids and meteors as well, were born in planetary upheaval, as electric arcs blasted material from the surfaces of planets and moons to produce fused formations identical in appearance to fused material in laboratory experiments with electric discharge. Here, an arriving comet moves on an elliptical path through the sun's electric field, an exceedingly weak field, but immensely powerful across the great distances of interplanetary space. As the comet draws closer to the sun, the charge imbalance triggers electric discharge, creating a coma and long cometary tail. The mysterious jets of comets can then be understood in terms of arc discharges to the nucleus, very similar to industrial electric discharge machining. The excavated material is accelerated into space along the jet's filamentary pathways. Intermittent and wandering arcs erode the surface and burn it black, leaving the distinctive scarring patterns of comet nuclei. The jets explode from the nucleus at supersonic speed and retain their coherent structure for hundreds of thousands of miles. Seen in terms of an electrically neutral vacuum in space, nothing of this sort should occur. The tails of comets reveal well-defined, twisting filaments extending up to tens of millions of miles without dissipating in the vacuum of space. For proponents of the electric model, this contradiction of neutral gas behavior is no surprise. It is the testament to the comet's electrified environment. The proponents of this interpretation also say it's the electric force that holds the spherical coma in place against the solar wind as the comet races around the sun. The diameter of the visible coma will often reach millions of miles, and it's surrounded by an even larger and more improbable spherical envelope of fluorescing hydrogen, visible in ultraviolet light. For decades, we've been assured that comets were made in the deepest of deep freezes in interstellar space. Comets coalesced from interstellar stardust, the primal material of the universe, before the emergence of the sun as we know it, or its planets and their moons. A foundational principle of comet theory, and of modern cosmology as a whole, is compositional zoning. At the outermost reaches of the sun's domain, formative processes were limited to the most rudimentary material, raw dust constituted in an environment close to absolute zero, with no complex chemistry. In contrast, bodies later formed close to the emerging sun would exhibit minerals formed at relatively high temperatures. For decades, this theoretical claim stood fast, and the claim was even carried into space. It's what prompted the Stardust mission to Comet Wild 2. As indicated by the very name of the scientific mission, the theory required that a comet be constituted of stardust. But the core assumptions of comet theory could not withstand the shock from the data returned by the Stardust mission. Launched on February 7, 1999, Stardust carried with it a tray of aerogel to capture samples of comet dust from Wild 2, and it returned these samples to Earth. Scientists could then view microscopically the raw material of a comet. The first surprise was the size of the dust grains, much larger, stronger, with far more complex structure and chemistry than theory allowed. And the gel did capture trivial amounts of the expected microscopic dust, invisible to the naked eye and leaving shallow, bowl-shaped pits in the aerogel. But more common by far were much deeper tracks, more in the shape of carrots than shallow pits. The particles themselves were clearly visible to the naked eye. To their amazement, the mission scientists found elaborately developed crystalline structures in the Wild 2 dust. It was an exciting discovery, but one that challenged all prior theory of a comet's origins. Crystalline structures cannot form in the absence of minimum temperatures, temperatures unavailable in interstellar space. The spectra of silicates in cometary comas were evident as far back as the probes of Comet Halley, though largely ignored. But the mystery couldn't be ignored after arrival of the comet Hale-Bopp in 1997. This comet's spectra placed an exclamation point on crystalline silicate structures in cometary comas. To get past the problem, astronomers hedged their bets. They surmised that billions of years ago, the raw material of the comet was ever so slightly warmed by an emerging sun. Then all of the discrete particles in a vast circle around the sun were transported outward by means only guessed at to the faraway and frigid Oort cloud. But this rationalization failed outright once the scientists had real comet dust in their laboratories. The grains were simply too large, and the mineralogical and chemical compositions far too complex. One puzzle was followed by another. Comet theory assumed that water ice was a primary constituent of active comets. But no water ice was detected on the nucleus of Wild 2, and not a trace of water was found in the well-preserved comet dust. And yet, paradoxically, the raw comet material of Wild 2 contained iron and sulfur minerals that can only be formed in the presence of liquid water. Liquid water, not in the near-perfect vacuum of deep space and not in a deep freeze. Instead of trivial warming, the Wild 2 minerals revealed a diversity of formative processes. Various sulfide minerals requiring liquid water can only exist below 210 degrees Celsius or 410 degrees Fahrenheit. These minerals have never seen higher temperatures. But also occurring in the comet dust was the mineral olivine, whose molecular structure rapidly breaks down in the very presence of water. It's a common igneous form, an abundant byproduct of volcanism. Perhaps the biggest surprise was that some of the comet minerals, such as forsterite, in the instant of their formation, were heated to thousands of degrees. Forsterite is formed in the most intense volcanic heating of silicates, but occurs also in lightning strikes to silicate rocks. The message could not have been more emphatic. It was not just the hypothesized Oort cloud that failed to work as advertised. The entire concept of compositional zoning, as applied to comets, failed its first acid test. Comet material requiring moderate temperatures in liquid water. Comet material formed at exceedingly high temperatures. Only the most trivial levels of the presumed raw material of comets, interstellar dust. A complete absence of water, despite cometary material originally formed in liquid water, though the olivine abundances could not have been formed or even survived in the presence of liquid water. And of course, liquid water requires atmospheric or other pressure. It cannot exist in the extreme vacuum of interstellar space. To this seemingly contradictory picture, we must add extreme selective heating. Selective heating because much of the compositional material could not survive the superheating that created olivine, forsterite, and other crystalline minerals. The Wild 2 discoveries have forced upon comet science one inescapable fact. In our own cosmic neighborhood, the diverse mineral content of Wild 2 is typical only of planets in the habitable zone of a fully developed sun. When the fundamentals of a theory are falsified by unexpected findings, a new vantage point is required, one that explains and predicts the surprises without introducing new contradictions. The conjectured Oort cloud freezer, forming and preserving comets for billions of years, is falsified by the Wild 2 findings. Only the diverse surface environments of rocky planets can provide the required raw material, and only the recent formation of comets can explain why these rapidly degraded objects are still with us. The bold question must now be asked: were comets created in recent periods of planetary instability and intense electrical events? Would minerals formed in liquid water then come as a surprise? Would comets now exhibiting no water be a surprise? Or crystalline structures suggesting igneous processes, or minerals pointing to the exceedingly high temperatures of lightning? A more unified picture of comet formation is available to us. And if comets were born electrically, what might the causative connection be to asteroids and meteorites, the apparent cousins of the comet? The Wild 2 mineral cubonite, a copper iron sulfide, is abundant on Earth and so too on Mars. In fact, it's found in Martian meteorites now known to have been blasted up to escape velocity from the surface of Mars, later to arrive at Earth. A few years ago, things now stated by astronomers would have been considered preposterous. Astronomers now acknowledge that the Martian moon Phobos, long called a captured asteroid, was formed out of material blasted from the Martian surface. For the source of a comet's constituent materials, planets close to the Sun's habitable zone are the most reasonable places to look. The foremost candidate is the planet Mars. In this intellectual adventure, we must revisit all earlier ideas about solar system history. Evidence for high-energy electrical events can no longer be ignored. The popular billion-year scenarios describing a comet's origins will be displaced by things now established as fact. and the changing picture of solar system history will surely not stop at the new story of the comet. Modern comet theory has long proclaimed that active comets are the result of sublimating ices. And yet the comet Wild 2 was active, though no water could be detected on its surface and none was found in the well-preserved comet dust returned to Earth. The theory requires cometary ices, and that's what scientists were certain they would find when the Deep Space One probe reached Comet Borrelly in 2001. But the probe could find not even a hint of water. In fact, an absence of detectable water on comet nuclei is the common finding. When astronomers discovered the fragments of comet Shoemaker-Levy 9 in 1993, they expected to observe volatile gases from sublimated ices, but no such gases were found. When comet Linear disintegrated, astronomers were shocked by the absence of water in the immediate debris, exactly as later occurred in the case of the disintegrating comet Elenin. But the momentum of theoretical claims is not easily overcome. When Borrelly's surface was found to be hot and dry, astronomers were not dissuaded from theoretical assumptions. Water must be emitted by the comet, even if not a trace is observed on the nucleus, not even at the very places where the jets erupt from the surface. But the mystery of missing water need not haunt comet scientists if they will question their theoretical assumption that water is necessary to create cometary displays. There's more to this mystery than common theory has even considered. Astronomers assure us that abundant water is detected in the luminous comas of comets. But this is where the real mystery begins. Cometary comas exhibit the hydroxyl radical OH. OH is not water, H2O, but just one hydrogen atom bound to one oxygen atom. Hydroxyl radicals can be produced from water molecules by photodissociation. When a photon of ultraviolet light from the sun strikes a water molecule, it can break the bond holding a hydrogen proton to the oxygen atom. If one of the hydrogen nuclei breaks free from the water molecule, what is left is the hydroxyl radical and a freely moving hydrogen proton, or positively charged ion. What comet scientists believe they see is water released from the comet's nucleus breaking down to produce the hydroxyl radical. They don't see the water itself. But that's how a theory interprets the presence of OH in cometary comas. And it does seem reasonable, except perhaps for the missing water on the nucleus and one additional mystery: the much greater accumulation of hydrogen than of OH in the comas of comets. These great envelopes of fluorescing hydrogen, entirely out of proportion to the presence of OH, suggest that something is happening around the nucleus of comets that the theorists have yet to comprehend. More than 25 years ago, scientists examining the comet Togo-Sato-Kosaka noted the problem. The ratio of OH to hydrogen was clearly too low if the original source was water. Here is a fact that has yet to enter official discourses on comet science. There is a simple and direct way to produce the hydroxyl radical in abundance, and it does not require water at all. Laboratory experiments by Nobel laureate Hannes Alfvén have shown that silicates, when bombarded by protons, produce abundant hydroxyl and other species found in cometary comas with no prior involvement of water. The experimental evidence points directly to charged particles from the sun, not light, and it directs us to the negative charge of the comet nucleus. The evidence for negatively charged comet nuclei has been with us for decades, since the Giotto spacecraft encountered Comet Halley in March 1986, discovering in the coma of Halley the negative ions prohibited by prior comet theory. In the electric model, comets on elongated orbits pick up negative charge while far from the sun. As they move into the sun's positively charged environment, electric discharge is the predictable effect. Electric discharge machining of the nucleus sputters negatively charged oxygen atoms from the surface. These negative ions then combine at some distance from the nucleus with solar wind protons to form the OH radical so prevalent in the coma. Numerous variations in the electrochemistry of the coma are certain to follow, and such reactions would be expected even when no water is present on the comet nucleus. The hydroxyl radical may not mean what astronomers have routinely assumed. The electrical interpretation places a new light on the surprising high-energy emissions of comets. It was only as astronomers began to view comets beyond the spectrum of visible light that they discovered the massive envelopes of more energetic emissions, including not just ultraviolet and extreme ultraviolet light, but X-ray emissions as well. In common human experience, ultraviolet light means an electrical event. It can be a natural emission of glow discharge or arcing in ultraviolet lamps and mercury vapor lamps. In intense electric arcs, UV emissions are always involved. That's why arc welders wear their protective masks, to shield their eyes from the ultraviolet emissions. To explain the surprising levels of UV emission, astronomers envisioned atoms of the coma reflecting or re-radiating UV light from the sun. But if comets are electric discharge phenomena, their remarkable glow in ultraviolet wavelengths could well be a new window to discovery. Recent telescopic explorations of space far beyond our own planetary system have revealed pervasive, explosive X-ray emissions, the one thing never expected in supposedly electrically neutral space. X-rays are close to the most energetic forms of light, well beyond the visible spectrum, with exceedingly short wavelengths. These emissions are created when high-speed electrons, moving at millions of miles per hour, release energy when striking an atom, or their course is rapidly altered by a magnetic field. Because of the energies involved in generating X-rays, only the rarest astronomer expected X-ray emissions from comets, due entirely to reflection of diffuse X-rays from an external source, the sun. One of the great discoveries in comet science came quite by accident on March 27, 1996. That's when the Rosat satellite detected highly energetic X-ray emissions from the comet Hyakutake, far beyond any astronomer's expectations. In the sciences, an event 1,000 times more energetic than expected is a call to reconsider theoretical assumptions. In July 2000, when the comet Linear disintegrated explosively, the Chandra Observatory confirmed profuse X-rays. In recent years, it's become clear that X-ray emissions from comets are business as usual for these bodies. But why? All theorists acknowledge that an electrical event is occurring, but the meaning of the event, the relationship between cause and effect, needs to be made more explicit. The electric comet model explains this occurrence by a strong electric field across the comet's plasma sheath. This sheath surrounds the negatively charged comet and isolates it from the more positively charged environment of the Sun. Where the sheath is most compressed in the sunward direction, it's not surprising that the electric field is strong enough to accelerate charged particles to X-ray energies. Without that electric field, nothing dramatic would occur. That's why in the debris cloud of the disintegrating comet Linear, we saw intense X-ray emission from the sunward face of the cloud. The emissions occur at the interface of the cometary coma with the more positively charged solar wind. The electric comet model predicts that all active comets will produce X-ray emissions. In an electric field, the required electron speeds can be achieved almost instantly. This fact was discovered over a century ago when Wilhelm Röntgen produced X-rays in his use of a Crookes tube. Both X-ray production and the fluorescence of neutral hydrogen around comets are readily explained by simple electrical events. Attempts to explain such behavior of comets in an electrically neutral environment will always require hypothetical effects more energetic than the conjectured cause. The single most critical test of the electric comet model came on July 4, 2005. That was when NASA's Deep Impact probe fired an 800-pound copper projectile at the nucleus of comet Tempel 1. Cameras on the probe recorded the event, and even the projectile itself contained a camera to transmit data up to the moment of impact. As early as 2001, looking ahead to this event, electrical theorist Wallace Thornhill began registering his expectations of surprises in store for comet science. On the evening of July 3, 2005, the day before the encounter, the Thunderbolt's website published the explicit predictions of Thornhill and his colleagues. These predictions would highlight the contrast between the standard and the electric comet models. As the Deep Impact probe approached Tempel 1, key NASA figures gathered in the control room. The comet was racing toward the probe at some 23,000 miles per hour when the probe launched its copper impactor toward the nucleus. If the comet was electrically charged, how would the electronics of the impactor respond to the electric field? Through most of its journey, the impactor's signal was clear, but in the final seconds, the signal was indeed disrupted. This apparent electrical disturbance was not all that Thornhill predicted. Also noteworthy was his expectation of an advanced flash ahead of the projectile's impact. This is exactly what occurred. And the advanced flash left NASA scientists scratching their heads. NASA scientists involved in the Deep Impact mission were well aware of the kinetics of impact explosions. But would the projectile be striking a solid, icy surface or a more loose aggregation of snowy fluff? What they did not anticipate, but the electric model explicitly predicted, was a major contribution from the electrical energy of the comet. The explosion would therefore be greater than any NASA scientist envisioned while working with electrically neutral conditions. It seems that the spectacular explosion that followed the impact was the greatest surprise. Every scientist viewing the live images expressed his astonishment. The scientists had expected to peer into a deep hole in a cometary dirty snowball before the Deep Impact vehicle was too far away. But the erupting cloud of silicate dust was so thick and the explosion so sustained that it completely obscured the local terrain. To the electrical theorists, the exploding cloud was a predictable effect. Fortunately, the Swift satellite provided a view of the comet explosion not just in visible light, but in ultraviolet wavelengths, which often give the best pointers to electrical events. The ultraviolet emissions required temperatures of over 3,000 degrees Fahrenheit. The temperatures of the blast will explain why the initial eruption saturated the sensors on the Deep Impact probe. Calculations based on pixel saturation indicated a minimum initial temperature of the flash at almost 6,000 degrees Fahrenheit. Though saturation means the temperature could have been much higher. The first purpose of the Deep Impact mission was to excavate the envisioned subsurface water ice. But electrical theorists have consistently predicted little or no water on most comet nuclei. Nothing approaching the expected levels of water was detected. Absence of volatiles as a dominant factor can only mean that something is fundamentally wrong in standard comet theory. The last resort in the search for water was the effort to identify the vents from which, according to popular theory, pressurized gases were escaping at the extraordinary velocities of Tempel 1's observed jets. The vents were never found. When viewed through the lens of standard theory, some predictions of the electric model could only appear absurd. Thornhill anticipated that the locations of the comet jets could actually shift as charge redistribution occurred on the nucleus after a significant electrical event. Confirmation of this prediction came from the Nordic Optical Telescope in La Palma, Spain. As released by the observatory, 2 images of the comet before impact and hours later tell the story emphatically. 15 hours after the blast, new jets appeared far from the location of the impact itself. The Deep Impact mission promised to give us the best images ever of a comet nucleus. On the eve of the impact, the Thunderbolts group stated the electrically predicted surface features in no uncertain terms. The surface of Temple 1 astonished the experts. Expansive mesas and steep vertical ridges did not belong on a comet, and the presence of craters sparked a debate that continues today. Fortunately, scientists had an opportunity for a second look at Temple 1. After the Stardust mission to Comet Wild 2, that probe was redirected to the object of the Deep Impact mission. Stardust was then renamed NEXT, or New Exploration of Temple 1. It would give additional views of the comet's surface. With the arrival of the NEXT probe, old mysteries only grew more perplexing, leaving scientists to debate the contradictions of theory. Even the scalloping of mesa walls and nearly vertical ridges, something we've mentioned so often in connection with electric discharge machining, was duly noted by NASA scientists. At least 60 craters were counted, though collisions along the comet's path would be exceedingly rare if occurring at all. And the surfaces of active comets are rapidly eroded, far too rapidly to preserve a record of rare impacts across geologic timescales. In fact, most astronomers now reject explanation by impact, and that includes Michael Ahern, the principal investigator of the Deep Impact mission. What then was responsible for the pervasive cratering of the Temple 1 surface? Laboratory experiments have shown that entire fields of craters are readily produced by electric arcs to a negatively charged surface. Nothing observed on cometary nuclei has contradicted the electrical interpretation. Here is the most fundamental question one could ask about active comets. Is electric arcing occurring at the surface? If so, should we not see this arcing where there is sufficient camera resolution? We have a good example in the energetic plumes of Jupiter's moon Io, where the sensors of the Galileo probe were saturated by apparent electric arcs, producing blotches of whiteout. A second example came with the Stardust mission and the appearance of small saturation points on the surface of Comet Wild 2, but with insufficient resolution to make a definitive case for what the electrical theorists suspected. The enigmatic whiteouts on the active surface of Temple 1 were everything the electrical theorists could have asked for, and the most prominent were placed exactly where the electric model envisions them. eroding the cliffs of mesa walls and extending the floors of numerous craters and depressions. And yet these extensive blotches of whiteout, while receiving occasional comments from the specialists, have yet to provoke any deeper curiosity as to their cause. But now, with a second look at Tempel 1, we can contrast the surface activity of the comet under two different circumstances. Deep impact occurred just one day before the comet reached perihelion, or its closest approach to the Sun. But the Stardust's next mission arrived 34 days after perihelion, as the comet retreated from the Sun and the electrical activity of the Sun itself was far below its activity at the time of deep impact. On July 2, 2005, 2.5 days before deep impact, the Space Weather website reported a remarkable surge in sunspot appearance, a direct indicator of surging solar activity. An active sun versus a quiet sun. For Tempel 1, this means different levels of proton bombardment a couple of days after the ejected particles left the solar surface. The contrast is remarkable. The more active comet presents an abundance of whiteouts. The less active, almost none. NASA scientists originally estimated that the Tempel 1 nucleus lost about 1/3 of a meter in depth with each orbit. But the electric model emphasizes selective and focused excavation. The new look at Tempel 1 showed that the most prominent mesa cliff had been dramatically excavated. The mesa was an estimated 15 meters high, and it had retreated some 50 meters. The most dramatic change on Tempel 1 occurred precisely where the pixel saturation was the most dense. The only remaining plausible explanation for pixel saturation on the more active comet is electrical erosion. NASA scientists also say that existing craters were extended between the two visits. 3 craters close to the dominant mesa had been further excavated to form a single trench. Electric arcs extend crater floors and erode the ridges of mesas and elevated terrain. The typical signature of both is the scalloping effect of rotating arcs. And it is no surprise to the electrical theorists that these processes energize a comet's jets. In fact, almost all of the jets of Tempel 1, when captured in its less active phase, are said to have emanated from the erosion of a prominent scalloped cliff. Selective erosion is a trademark of electric discharge machining. Before the deep impact projectile was fired at the comet, scientists were confident it would strike a dirty, snowy surface, penetrating well below the surface to excavate deep material. That's how the mission would expose the primordial stuff of comet creation. What would this deep crater look like? Of course, if the projectile struck a rock or discharged above the surface at an electrical event, the target area might look a lot different. Then the removed material would be silicate dust and debris, but with very little penetration beneath the surface. facilitate the investigation after a subsurface explosion, the Deep Impact Probe targeted the space between two well-identified craters. So in the return to Temple 1, mission scientists knew exactly where to look. But almost nothing could be seen, and certainly there was no resemblance to the deep crater the scientists had envisioned. To identify the crater location, the scientists published a view of the region with a circle of arrows around the impact site. How are we to understand the absence of a deep crater? On this question, the investigation appeared to move into weird and theory-defying science. A typical comet's gravity is perhaps 1/billionth that of Earth. Mere walking speed would be sufficient to escape the nucleus altogether. How would accepted theory allow material exploding from the comet at thousands of miles per hour to return to its finite point of departure and to refill the crater? A key to our understanding of the deep impact events is water production in the coma of an active comet. Abundant water, or hydroxyl, in the coma of Temple was readily confirmed, though NASA investigators saw only trivial levels of water on the surface. According to the scientific reports, the observed jet and coma activity of the comet would require 200 times more exposed water ice on the surface than was actually detected. This fact could only accentuate the absence of any vents to the previously supposed pressure chambers beneath the surface. No theoretically acceptable cause could be found for the energies of the comet jets. And nothing was observed that could account for the abundant hydroxyl or water in the coma. But this dilemma is removed by the electric comet model. The model explains the absence of water, the energies of the jets, and the absence of vents to subsurface chambers. And the presence of hydroxyl and water in the coma, but not as a general rule on the surface or beneath the surface, is a prediction of the electric model. The evidence points to high-energy electrical exchange. Electrically sputtered silicates from a negatively charged comet nucleus transacting with the charged particles of the solar wind. Water production through the electrochemistry of charge redistribution. The paradox of trivial surface ice on Temple 1 then finds a coherent explanation. The surface ice was produced electrically in the coma. Meager amounts of this water ice later drifted from the coma to the surface, condensing as a few shallow patches of frost. It's the hydroxyl radical that gives us the persuasive answer. Investigators thought they saw an injection of water into the coma from the nucleus several days after the eruption of dust had returned to normal. But that conclusion arose from an unsupported assumption. Based on data from the SWIFT satellite, investigators from the UK and US reported a spectacular increase in water content within the coma. But that increase did not begin until 5 days after deep impact, when the normal production of 16,000 tons per day increased by at least 250%, continuing for 5 more days. As reported, the rise in water content of the coma all occurred with no increase in dust content. No increase in dust. That's the fact that precludes the investigators' interpretation. Comet outbursts are never dust-free. In electrical terms, the rapid increase in hydroxyl or water would predictably come days after deep impact. And this is why the comet's X-ray emissions continued to grow. Above the nucleus, highly energetic, explicitly electrical events created a flood of X-ray emission, and the water of the coma was the byproduct of that electrical exchange, not the cause. A reconsideration of water production and its direct link to a comet's X-ray production is now essential. In fact, the contribution of charged particles from the Sun to comet activity is now acknowledged. It happened in 2012 when the distinguished Russian astronomer Suban Ibadov's paper appeared in the journal Advances in Space Research. Professor Ibadov's paper described a comet nucleus responding to charged particles from the Sun. His calculated capacitor-like discharges were equivalent to observed energies of comet flaring in ground-based observations of comets. Now that the door has been opened to discussion of the Sun's electrical role in comet discharging, how long can that role be overlooked in comet investigations? Taken as a whole, the message of deep impact is remarkably consistent. But why did the crucial findings all come as a surprise to comet scientists? And what does it mean that these surprises were the explicit predictions of the electric model? Deep impact provided us with a stunning confirmation of the electric comet, confirming as well the larger electrical environment of the Sun. Converging evidence from every line of investigation makes clear that the space sciences will be forever changed. Perhaps no flyby of a comet produced more instant surprises than the visit to Comet Hartley 2 in early November 2010. The visit was achieved by the original Deep Impact probe, subsequently renamed Epoxy for its encounter with Hartley 2. Even the shape of the comet caught investigators by surprise. The awkward bookends or double lobes made no sense. Astronomers likened it to a pickle, a peanut, a dog bone, and a bowling pin. Why would accretion of a dirty snowball or icy dirt ball from a homogeneous primordial cloud produce such a remarkable configuration? Standard accretion theories never envisioned anything of this sort. The theories always claimed that comets preserved the original raw material out of which the Sun and planets slowly accreted over billions of years. Hartley 2 revealed a split personality. Astronomers were in disbelief when they discovered that the two lobes exhibited radically different compositions. That finding flatly excluded prior assumptions and eliminated the imagined Oort cloud of earlier theory. One end of the comet was highly active and the other much less so. But why? The primary outgassing of Hartley 2 was coming from the smaller lobe. Astronomers were forced to a highly incongruous conclusion that the two end pieces of the comet formed separately in much different regions of the solar system. And here again we meet undeniable evidence of a common history for planets and comets, both forming from well-differentiated materials in the habitable zone of the Sun. A collision of two comets in the vastness of the heliosphere would involve the most extreme improbabilities. And if two small comets originated in much different regions of the solar system, how likely would be a merging by gentle collision? The strangely smooth waste of Hartley 2 seems to have invited extreme speculations from NASA scientists. A comet just a mile wide would have no appreciable gravity. But could gravity have nevertheless guided dust from the ends of the comet toward the waste? The electric model does not force scientists to such conjectural extremes. Electrostatic deposition is well established in environments of electric discharge. The spectacular jet activity of Hartley 2 continues to haunt comet scientists. Jets erupted from the sunward face of the comet, but could also be seen exploding from regions in shadow with the same force as those exposed to sunlight. What was driving the velocities of Hartley 2's jets? Traditional theory has always explained cometary jets through both surface and subsurface warming. Surface sublimation in areas of brightness or exposure to the sun alone would not be sufficient to drive the high-speed jets. Subsurface pressure chambers are a requirement. Investigators found that dust and carbon dioxide were being emitted by the comet in consistent proportions. This led them to the conclusion that CO2 pressures building up in chambers beneath the surface were driving the explosive jets and in the process carrying dust along with them. Fortunately, Hartley 2 investigators could trace the jets to topographical features. But these features did not include the expected openings to subsurface chambers. Without the required pressures, the acceleration of material away from the comet would have no identifiable cause. In the vacuum of space, a mere surface response to light from the sun would involve virtually no pressure at all. Here's a remarkable fact reported by NASA investigators in September 2010. Prior to the arrival of epoxy, Hartley 2 produced an immense cloud of cyanide or CN gas. The explosive increase in cyanide occurred over a little more than a week, an event investigators dubbed the CN anomaly. Typically, during the ebb and flow of a comet's activity, we see a consistent proportion of removed dust to the gases emitted. But the epoxy probe detected no dust increase at all. Equally stunning was the fact that the cyanide increase did not show up in the comet's jets, though this is exactly where one would look to identify a source if the source was in fact on the nucleus. Is it possible that the cyanide abundance did not originate from the surface, but from the electrochemical activity in the coma? Could electrical exchange between a highly active comet and charged particles from the sun resolve the mystery of cyanide production? To clarify this issue, we consulted with Dr. Franklin Anariba, an electrochemical researcher and lecturer at the Singapore University of Technology and Design. Dr. Anariba agreed to explore the question, and we subsequently invited him to present his findings at the recent Thunderbolts Project conference in Albuquerque, New Mexico. In his investigation, Dr. Anariba found that electrochemical events could account for several key features of comets. These would include plasma generation in the coma, the observed hydrogen gas cloud surrounding the comas of comets, dust tail formation, the ionized plasma tails of comets, and gas production within the comas of comets. Electrochemistry requires a voltage difference, and the coma of Hartley 2 was well suited for the electrical production of water, cyanide, and a good deal more. As for cyanide, the confirmed presence of methane and of ammonia would be quite sufficient. Add electric discharge and cyanide would be the byproduct. Hartley 2 is a hyperactive comet with a continuing potential for surprises and anomalies to standard comet science. But when is a mystery really a mystery, and when does it mean the breakdown of an onboard instrument? As pointed out to us by Dr. Anariba, NASA investigators recently announced that the so-called CN anomaly was actually an instrument failure. It appears that no further analysis of the claimed failure has been made public. Did an instrument really fail to perform properly, or did speculation take over when the standard theory could not account for a recorded event? Either way, the electrochemistry of cyanide production in the comas of comets is a crucial issue that must be explored. December 2010, Russian astronomer Leonid Elenin announces the discovery of a new comet, roughly 400 million miles from Earth. Calculations show that the comet, moving on a highly eccentric orbit, will intersect the orbit of the Earth. Based on the size of its coma, most astronomers viewed the comet as typical and unexceptional, suggesting a body 2 or 3 miles wide. But the projected Earth-crossing orbit sparked an outburst of internet rumors and doomsday predictions. Most remarkable were the suggestions that the comet was a rogue planet, and claims that it would profoundly disturb the Earth, causing earthquakes or a shifting of the poles, and even the end of the world. Respected astronomers were dismayed. How could such scientific illiteracy attract millions of viewers to internet articles and videos? Experts reminded us of the trivial mass of a comet just 2 to 3 miles wide, passing millions of miles from Earth. As it turned out, what actually happened to Elenin posed a profound mystery for comet science. In the summer of 2011, Elenin grew brighter than expected, and astronomers began to anticipate a respectable show. But the situation changed when a powerful coronal mass ejection erupted from the Sun. On August 19th, the CME struck the comet Elenin. The comet flared brightly, appearing to disintegrate explosively while rapidly dimming before it was visually lost against the glare of the Sun. On October 24th, only days after the expected closest approach to Earth, Italian astronomers captured the remains of Elenin on film. An extremely faint and diffuse cloud of dust was all that could be seen. How did the disintegration and virtual disappearance of Elenin occur? The answer appears to lie in the role of charged particles in an electrical event. When the charged particles of a coronal mass ejection struck the comet Elenin, the oppositely charged nucleus could not withstand the electrical stresses. It disintegrated like an exploding capacitor. The electrical theorists assure us that comets are not what we were taught in school. No practical experiment ever demonstrated that a dirty chunk of ice would disintegrate explosively under gentle warming from the Sun. The explosive demise of comets cannot be due to solar heating. In fact, eruptions and comet disintegration have occurred in regions so remote from the Sun that warming is not even a factor. We saw one of the most improbable flarings in the case of Comet Halley, a regular visitor to the inner solar system. In 1991, 5 years after Halley's closest approach to the Sun, it was well beyond the orbit of Uranus, where temperatures hover around minus 330 degrees Fahrenheit. It erupted, producing a dust cloud 180,000 miles across. If thermal stresses are excluded, it seems that only one consideration remains. Shortly after the Halley outburst, a few astronomers began to wonder, could charged particles from the Sun be a factor? At the time, solar wind activity had peaked at a higher level than had been seen in decades. Then 2 astronomers observed that the charged particles of a powerful solar flare on January 31 would have likely reached Halley around February 12, the date of the outburst. The coincidence of the outburst with that arrival seemed too great to dismiss. Could electrical events be the key to comet outbursts and fragmentation? To this day, astronomers have no explanation for the sudden and spectacular brightening of Comet Holmes in 2007. It had been moving rapidly away from the Sun for about 5 months when its coma size suddenly grew by a factor of 1 million, making it even larger than the Sun. Was it a coincidence that just 2 days before the comet's display, there was a sharp spike in the output of the solar wind? In the electrical view, the sudden arrival of charged particles from the sun will explain what otherwise would have no known cause. Electrical surges and capacitor breakdowns go together. High-tech image processing later showed that the nucleus of Holmes had broken apart, with many fragments contributing to its brightening, confirming a general pattern. Comets flare brightly when breaking apart. In 1976, Comet West brightened greatly in a series of outbursts, perhaps a dozen or so, then shocked astronomers by breaking into fragments. Warming by the sun is not a reasonable explanation of such events. When Comet Virtanen fragmented in 1957, it was just inside the orbit of icy Saturn. Much the same occurred in the case of Comet Biela-Bamberg. More than once, comets have broken up at their greatest distances from the Sun, well beyond the orbit of Neptune. And when breakup occurs, the fragments have separated at inexplicably high velocities. Mainstream theory has no explanation for the energies driving such events. The progressive disintegration of the comet Schwarzmann-Bachmann 3 beginning in 1995 left astronomers grasping for answers. Though 150 million miles away, it brightened spectacularly, shining hundreds of times more brightly than expected. Then astronomers discovered that the comet had broken into at least 4 pieces. Then, in 2006, the Hubble Space Telescope captured the spectacular disintegration of the comet in progress, while it was still out beyond Earth's orbit. It was then clear that the comet had broken into more than 36 fragments, as house-sized chunks of the comet appeared to disintegrate completely, some within the span of a single day. Remarkably similar to the fate of Elenin was the explosive demise of the comet Linear in July 2000. Like Elenin, Linear entered the inner solar system from its outermost regions on a highly eccentric orbit. For the electrical theorists, that means a maximum change in the electrical environment. As it approached its perihelion some 70 million miles from the Sun, it flared, then rapidly disintegrated. The disintegration of Linear provides a strong parallel to the story of Elenin. The teardrop form of the flare and the relationship of the flare to disintegration are virtually identical. All that was left of Linear was a cloud of dust. The expected abundance of water was simply not there. And what of Elenin? As reported by Leonid Elenin himself, the expected water vapor was missing. If charged particles from the Sun are triggers for outbursts or disintegration of comets, the behavior of these bodies has almost nothing to do with relative masses or surface temperatures, and everything to do with the electric force. Is it possible that one question could remove the anomalies? That one answer could explain the flaring, the fragmentation, and the catastrophic demise of these cosmic intruders? In the electric universe view of comets, these bodies were excavated from planetary surfaces in an epoch of cosmic violence. From this vantage point, even asteroids and meteors originated in the same or similar events. Electrical theorists have gathered many volumes of evidence to show that planets once moved on much different courses than today. In violent encounters, planets were immersed in electric discharge as stupendous arcs passed between these charged bodies. Electric arcs acting on planetary surfaces and on the resulting dense clouds of dust and debris fused material into the unique shapes of comets and asteroids, including the double-lobed forms often observed. Was Comet Hartley fused into its odd shape by electric discharge? In one of the first electrical experiments by plasma scientist C.J. Ransom, the fusing of surface material produced a near-perfect replica of Hartley II's unique morphology. The only appreciable difference was in the relative sizes of granular material, as we'd expect. Could this remarkable similarity be merely accidental? At Hartley II's smaller end, mission scientists observed what they called shiny clumps or cubicles reaching up to 16 stories tall. They were not just oddly configured. They were 2 or 3 times more reflective than other surface materials. But look again at the Hartley II counterpart produced in Dr. Ransom's experiments. Here we see materials fused electrically into shiny, more reflective clumps, giving us the very answer that NASA scientists missed. Fusing of material into glassified texture will multiply reflectivity. And so the mysteries of comets deepen, and the most urgent need is to reconsider the nature of comets as a whole. It seems that anomalies are just too easily ignored or forgotten, but recurring anomalies can be the door to discovery. What better way to move science forward than to ask the question, what is a comet? Popular astronomy has long imagined comets to be dirty chunks of ice moving through electrically neutral space. But a growing number of electrical experts see comets as charged bodies responding electrically as they move more deeply into the electric field of the sun. One question leads inexorably to another. How are comets formed? What holds the spherical coma in place against the force of the solar wind? How are the long filamentary tails created and maintained in the extreme vacuum of space? What force creates and confines the powerful collimated jets from the nucleus? What is the source of the intensely energetic X-ray emissions? Spacecraft have now visited a half-dozen comets, and popular theory cannot withstand the surprises that followed. The collapse of theory began with the visit to Comet Halley and the discovery of forbidden negative ions close to the coma of the comet. Astronomers were stunned to find that the bone-dry surface of Borrelly was the opposite of the dirty snowball expected. Then the foundations of the Oort cloud theory were overthrown by a series of discoveries, beginning with the recovery of comet dust from Wild 2. The dust could not be distinguished from the diverse materials of planets in the habitable zone of the Sun. In 2005, we fired a projectile into the nucleus of Comet Tempel 1. The outcome of that comet visit contradicted every theorist's expectations while confirming the explicit predictions of the electric comet model. Disruption of radio signals from the impactor, the advanced flash, the astonishing energies of the impact explosion, the sharply carved surface of the nucleus, direct evidence of surface arcing, the changing jet positions, the overwhelming dominance of dust, not water, in the immediate explosion. Then we returned to the comet in 2011 and found that the excavation of mesas and ridges on the nucleus had occurred exactly as the electric model has long claimed. We visited the highly active comet Hartley 2 in 2010. For the electrical theorists, the findings that so surprised and perplexed mission scientists were in no way surprising. The radically different composition of the two lobes of the nucleus, the jets erupting from regions in shadow, the absence of vents to the imagined subsurface pressure chambers, the smooth dust-covered waste, and the shiny cubicles on the surface all point emphatically to the electric comet. Decades of comet exploration have now demonstrated beyond any reasonable doubt the inseparable connection of comet activity to electrical attributes of the Sun and its domain. The erratic flaring of comets and the explosive disintegration of such bodies occur naturally in the Sun's electric field, and particularly in response to a sudden increase in charged particles ejected by the Sun. Nor can comet science afford to ignore the experimental evidence. Most significantly, the ability of electric arcs to create the extraordinary morphologies of comet nuclei and their cousins, asteroids. Our understanding of comets is already and forever changed, and this new perspective does not stop with comets. Verification of the electric comet will eventually touch everything we thought we knew about the cosmos, about solar system history, and about the history of our own planet, Earth.